Hi dear students, welcome to my channel. In this video, we will discuss nuclear reactor design basics by one famous book by Glasstone and Sesonske. There are two volumes. First volume, he completely discussed about nuclear reactor design, radiation protection and materials. In the second volume, he focused process related heat transfer, heat transport from the fuel and fuel management and reactor operation point of view and reactor safety. In the first volume, chapter wise we will discuss. The first chapter is energy from the nuclear fission reaction. So to understand every concept clearly, first we should and must thorough with fundamentals. First I will give you a brief introduction about this nuclear reactor program. In 1939, the fission reaction discovered by Enrico Fermi. In fission reaction, it releases huge amount of energy. So that energy can be utilized to produce the electricity. In 1939, they discovered the fission reaction. In 1950 onwards, they started building, constructing nuclear reactor and producing the electricity. Now, entire world, the most of the countries, they are producing electricity by using nuclear reactors. The most advantage of this nuclear reactor is there is no carbon dioxide emission. Another thing, for simple comparison, I will tell you, if you are producing the electricity by using fuel, that is coal fuel, and the fuel what you are using in nuclear reactor is uranium. So natural uranium, simple comparison I am telling. Approximately 21,000 kg of coal, how much power produces? Just 1 kg of natural uranium produces equivalent of power. This single information is enough how efficient is nuclear reactor. Now we will come back to the fundamentals of nuclear energy. So before going to in the details of nuclear design, first you should know the fundamentals. The first thing what you should know, ultimately atom, atomic structure and isotopes I will discuss. Atom, that you know, atom composed of electrons, protons and neutrons. Centermost portion of the atom is the nucleus. Nucleus contains nucleons. They are protons and neutrons. Okay. Number of protons in an atom we are calling that is atomic number. Number of protons plus neutrons we are calling that is a mass number. Proton is positive charge, electron is negative charge. Atom as a whole is a neutral. This you know. Okay. So what is the importance of this I will explain. So you know, in the nature there are 92 elements available. 92 element, the 92 element is uranium. Okay. So these 92 elements, the properties are different. Okay. So when you are calling this atomic number is nothing but number of protons. The proton is a positively charged particle. This positively charged particle repel another positively charged particle. So because of this what happens? The proton-proton repulsion takes place and instability come into the picture. Okay. Then how the nucleus is stable? That part also you should understand. Now this atom you understood and nucleus you understood, and to calculate the energy released in the nuclear process, we need to have some shortcuts or some standard rules to follow to solve the or estimate the how much energy released in the nuclear reactions. Okay. Now I will come to the fundamental mass number you know, atomic number you know, and isotope I should tell you. Isotope means same proton number, same atomic number. Suppose uranium 234, uranium 235, uranium 238, 3 isotopes, same atomic number, different mass number, that you know. Okay, that is isotope. Now I will explain you regarding the basis of atomic mass scale or atomic weight scale. What you know atomic weight scale means, if I ask you carbon is there, carbon 12. Carbon 12 means 12 is a mass number, 6 protons and 6 neutrons, that you know. So what is the atomic weight of carbon 12? What you tell? It is 12. Why it is 12? Actually 12 is what? So for that I will explain you what is the basis to consider this 12 as atomic mass. What is the basis we are using for atomic weight scale? Okay, up to 1962 we were following oxygen 16 as basis for atomic weight scale. So oxygen, there are 3 isotopes, oxygen 16, oxygen 17 and oxygen 18. So out of 3 isotopes, oxygen 16 is highly abundant. After 1962, we were following carbon 12 as basis for atomic weight scale. Basis means everything is measured in terms of weight of the carbon. That's why it is a basis. Okay, why they switch over? The main reason is the actual atomic weights from the mass spectrograph, what they measured, the atomic weights of different atoms, the error is coming less when you are considering carbon 12 as basis for atomic weight scale. So that's why after 1962 onwards we are following carbon 12 as basis for atomic weight scale. Okay, now I will come back to some basic concepts related to mole. 1 mole means what? 1 mole of oxygen, 1 mole of carbon dioxide, 1 mole of nitrogen. They contain one standard fixed number. That number is Avogadro number. Not only these 3, you take any gas, any entity, any atom, any molecule. If it is 1 mole, it should and must contain Avogadro number. Oxygen 16, 1 mole means 16, oxygen 16, 1 mole means it contains 6.022 into 10 to the power of 23 atoms. Suppose nitrogen, you take nitrogen gas is there, molecule I am taking now, N2. 1 mole of N2, it contains 6.022 into 10 to the power of 23 N2 molecules. So this is Avogadro number. So why I need this? So I want one basis for the calculation of nuclear energy, one atomic mass unit. Atomic mass unit I am using to calculate what is the energy releases in nuclear reactions. So how this atomic mass unit is derived, I will explain you. Okay, carbon 12 grams of carbon contains 6.023 into 10 to the power of 23 atoms. Okay, now I want what is the mass of 1 carbon atom. 12 grams contains 6.022 into 10 to the power of 23 atoms. So 1 atom is equal to 12 grams divided by 6.022 into 10 to the power of 23. That is Avogadro number. 12 divided by Na. Na is Avogadro number. Okay, this is mass of 1 carbon 12 atom. Then atomic mass unit is defined like this. Atomic mass unit equal to 1/12 of carbon 12 mass. Carbon 12 mass you calculated now, divided by 12, that is 1 atomic mass unit. It is equal to approximately 1.661 into 10 to the power of minus 27 kg. This is 1 AMU, atomic mass unit. You understood, no? So in the calculation, this term most frequently appears. So that's why first I'm making you ready to use this and to solve the problem. Atomic mass unit you understood. From the special theory of relativity, Einstein's equivalence of mass and energy. It means you can convert mass into equivalent of energy. If one mass m is there, if you want to convert into energy into c square, mc square. C is the velocity of light in vacuum. So if mass m quantity, equivalent of energy is mc square. So this mc square is energy of that particular mass. So I want to convert this energy into one unit, that is mega electron volt. Actually unit of energy that you know, that is joule. Okay. So mc square, if I'm giving m equal to 1 kg, c is equal to 3 into 10 to the power 8 meter per second. You do calculations, you will get answer in terms of joules. You convert into electron volt. 1 electron volt is electron charge, you know, 1.602 into 10 to the power of minus 19. So energy acquired by electron when it will move in a potential difference of 1 volt, that is called 1 electron volt. So by using this you can convert that joules into electron volt. Now I am coming back to the one atomic mass unit. If you convert into equivalent of energy, that is equal to 931.3 mega electron volt. Remember this. 1 AMU, 1 atomic mass unit, equivalence of energy 931.3 mega electron volt. Approximately you can round off to 931 mega electron volt. You understood, no? This part is clear. These are the fundamentals you should and must know. Okay. Now you go back to the nuclear stability and binding energy. Before that we will calculate binding energy. What is the binding energy? Binding energy of what? Now you see, simple example, carbon 12. It contains 6 protons, 6 neutrons and 6 electrons. Okay. Proton mass, neutron mass, electron mass, you know it. So 6 m into p, mp. Matlab, proton mass is mp, neutron mass is mn, electron mass is me. So 6 mp plus 6 mn plus 6 me. That is the total mass. Agree? Total mass of the carbon 12 supposed to be like this. Now you measured carbon 12 atom mass. It should be same. 6 proton mass plus 6 neutron mass plus 6 electron mass should be same as carbon 12 mass. But it is not so. It is not so. Something is happening. Why it is? So there is a mass difference. The sum of the constituent particles, the fundamental particles, sum of the masses of constituent particles of an atom and the atom mass. If you subtract, you will get some value. This is called mass defect. Then why it is coming? Now you see carbon 12, 6 protons, 6 neutrons, 6 electrons. These are all bounded to each other. They are bounded to atom. So these proton neutrons are bounded inside the nucleus. Electrons are outside, but as an atom together, all are bounded. They are not free. Okay, they are specified to move in particular direction, in particular location only. They are all bounded. Now I will supply some energy to this carbon 12 atom so that all particles are free from each other. All protons, all neutrons, all electrons will free from each other. They will move. So I am supplying some energy to that. Okay. Now 6 protons separately I will bring, 6 neutrons separately I will bring, 6 electrons I will bring. I will join them to form carbon 12. Now what happens? It releases the energy. Initially you supplied energy to free from each other. When you're joining them, how much energy you supplied, same amount of energy is coming out. Why it is so? From where this energy is coming? When I supply the energy to free them, what happens to masses? When neutron is inside the nucleus, what is the mass? When neutron is free from the nucleus, what is the mass? When these nucleons or fundamental particles are free from each other, the mass is more when they are in bounded state. When the neutron is inside the nucleus, that neutron mass is less when it is free. That is why this binding energy coming into the picture. So the mass defect is again a mass. Equivalence of energy. Mass defect, it is a mass. Equivalence of energy is called binding energy. Okay. Now binding energy per each nucleon I want to calculate. What are the nucleons which are inside the nucleus? That is proton and neutron. Carbon 12 nucleons are there. So this binding energy divided by mass number, that is called binding energy per nucleon. If binding energy per nucleon, why we want? Why we should learn this? So based on binding energy per nucleon, you can judge which is stable, which is unstable. Can you guess which is stable? If it is higher is stable or lower is stable? Certainly, if binding energy per nucleon is higher, that nucleus, that atom is stable. Okay. Now you understand what is mass defect, what is equivalence of energy, what is the binding energy, what is the binding energy per nucleon. Now we will compare all the atoms, naturally available atoms in the nature up to 92 atomic number only. So up to uranium only they are available, you know, from hydrogen, helium, lithium, beryllium, boron, that all. Okay. But in the nature up to 92 only they are available. Remaining all up to 92 they are artificially made. Okay. Then second part, what you have to discuss? Nuclear stability you should discuss. First you understood what is atomic structure. Next, what is the binding energy? Now you should understand what is the nuclear stability. Stability means it is stable or not. Up to what atomic number it is stable. What happens if atomic number is increasing? Atomic number means number of protons. Means number of protons are increasing. Will it be stable or not? From what atomic number this instability going out? Instability is coming, going out. So after what atomic number the atom is no more stable. That part we'll discuss now. Now why it is happening, first you should understand. You go for the nucleus only, not for electron. Electron mass is very small compared to the proton neutron mass. You don't consider now. A nuclear point of view, you don't consider the mass of the electron in the calculation because its value is 1 by 1837 times mass of proton and neutron. So I can neglect it. So I am talking about binding energy per nucleon means for nucleons like proton neutron only. Okay, now you see when atomic number is in, atomic number means hydrogen specific nature. Hydrogen contains proton and electron only. There is no neutron. That is the beauty of the hydrogen. It contains only proton and the electron. There is no neutron in the hydrogen. In helium, 1 proton, 2 protons, 2 neutrons. Lithium, 3 protons, 3 neutrons. So except the hydrogen, remaining atoms contains 1 or more neutrons. Okay. This proton is positively charged particle, that you know. So atomic number is increasing means number of protons are increasing. Number of protons are increasing means the repulsive force, electrostatic repulsive force increases. So instability increases as atomic number is increasing. But still it is stable. Carbon 12 is stable. Oxygen 60 is stable. Even though oxygen contains 8 protons, still it is stable. Why? What makes that protons do not come out from the nucleus? Something else is there which is combining these nucleons together. That is intranuclear forces. These intranuclear forces are short range forces. These forces are effective up to a distance of 10 to the power of minus 15 meter. You imagine how small it is. If nucleons means proton and proton, proton and neutron, neutron and neutron together with a distance 10 to the power of minus 15 meter, this intranuclear forces are dominant. They are attractive forces. These intranuclear forces bind nucleons means it will attract one proton with another proton, neutron, neutron, proton, neutron. So this intranuclear forces dominant over the electrostatic repulsion between the protons. That is why this nucleus is stable. Okay? Then it is stable up to some value. As atomic number is increasing 10, 20, 30, 40, 50, 60, 80, 90. When atomic number is 10, atomic number is 50, it is not same. Atomic number is 60, 50, more protons are there, electrostatic repulsive force is dominating, means increase hota hai. So as atomic number is increasing, this instability increases. For that, we have some relation between the number of neutrons and the protons in a particular nuclei. N by P ratio, neutron to proton ratio. Based on that value, certain nuclides are stable. If number of neutrons are more, suppose protons are 10, neutrons are 15. So in this case, the neutrons are more means intranuclear forces are more. So neutrons increasing, they are more than the protons. That is why this intranuclear forces dominant, they are making stable. Okay, but this you can see in the book, that one graph is there. X-axis is proton, y-axis is neutron, n by p, one straight line is there. But n by p straight line means neutron equal to proton, that is straight line. Okay, but neutron is more than proton, that is a stable. So you can see the book, you can very well understand the region above that line, the neutron should be more than the proton. So that nucleides are stable. They have given some numbers, magic numbers for protons and neutrons inside the nucleus, that you can very well know it. That is 2, 8, 20, 50, 82 proton number, 2, 8, 20, 50, 82 and 126 neutron number. If it contains this number as proton and neutron, they are the stable. Okay, it is just like in electronic shells, they 100% fully filled inert gas, no, they are chemically how they are stable. Similarly in the nuclear, inside the nucleus also, this nucleus fills the energy shells fully filled, that is stable. If you go for nuclear model, that you can understand, but that much is not required for you. So this much only you just understand, and ultimately we are going to construct the reactor, design the reactor and operate the reactor. That is our target. But this much you understand, the magic numbers which contains proton, neutron, they are the stable. Okay, this part is clear. Now stability, nuclear stability, that you understood, and binding energy you understood, some isotope, the basics of the nuclear reactor you understood. Now one more thing I should explain you, that is the neutron reactions. The neutron which is coming from the nucleus, The neutron coming out with higher kinetic energy. It can interact with the medium, other particles. The interactions are three types. One is the scattering, another is capture, and the third one is fission. The scattering means the particle, the neutron is coming and hitting, and it is moving another direction. The scattering means the kinetic energy exchange is taking place between the neutron and the other atoms or the medium of the atoms. This scattering two types. One is elastic scattering, another one is inelastic scattering. Elastic scattering means kinetic energy is conserved. Inelastic scattering means some part of the kinetic energy of the neutron is given to the nucleus of target atom or medium. The target atom neutron is going and hitting one atom. Inside the atom nucleons are there, no? Some energy, some part of the energy given to the nucleus. Within the nucleus, that nucleons will be in excited state. So the potential energy of the nucleons inside the nucleus is increased. It means some part of energy is given to the inside the nucleus. In this case, the kinetic energy is not conserved. That is why it is inelastic collision or inelastic scattering. Okay. Now second one is capture. Capture means the neutron is absorbed by the one nucleus and it will release some energy as an electromagnetic wave, gamma rays. That is capture. So the atom absorbing the neutron, it is forming a compound nucleus and releasing energy as an electromagnetic wave. That is called capture. The third one is the fission reaction, which is most important. In this entire nuclear reactor, the fission reaction is most important. We are going to deal in the next class. This fission reaction I will explain in the next class. Till next class, bye bye.